but let us get the fundamentals of gas. So we will look at where does the gas come from, how does it evolve, and how does it go out. Okay. So first part of gas coming up is from the gas evolution from the metal itself, and then that gas, if it is not vented properly, it creates a blowhole. So we worry about how blowhole is formed. One more thing which happens as metal flows and starts solidifying is a lap formation, which happens in some castings. We look at that, and finally look at venting and effect of venting on the air escape and so on. So this is one experiment which we are going to show you. So this we have created a small transparent mold in perspex, and we fill the thing with water, and we create an artificial vent on the top of the casting, and as it and we have done it in slow motion yesterday. So we are going to show you the movie separate. Maybe in the break I will show you the movie to you. But it's very interesting to see that how metal comes in, or this water of course, but how water comes in, how bubbles are formed, how the venting is taking place, and so on. So we'll see it when we do that. But first, what are the sources of the gas in the metal here? One is your entrapped air of the mold cavity itself, that we know. Second is the moisture in the mold, which becomes steam, that also we know. Third is the combustion of the resins and binding materials of the mold materials. Then you have the gas evolution or diffuse gases in the metal itself, which got into the metal when you melted that, and now they are coming out when the metal is solidifying. They are the 4 or 5 sources of gases in the mold cavity, and all of these have to come out, otherwise you have gas porosity and blowholes. How much gas really we are talking about? If you look at aluminum alloys, which is what absorbs the largest amount of hydrogen gas, where does hydrogen come from? Moisture in the air and moisture in the, let us say, mold. Okay. Look at the number of the value here. At the melting temperature, let us say the top blue one, the amount of gas absorbed is almost 60 milliliters per kg. But the absorbability of that same gas, once the temperature falls to room temperature, let us say 20 or let us say 7 degrees after solidification, is hardly 10 milliliters, which means it absorbs something like 6 to 7 times the volume of gas, and that volume has to come out. And 50 milliliters of gas per kg is not a small amount. Finally, it all becomes gas porosity and goes into the metal. So unless you do degassing properly, okay, unless degassing done, so dry furnace, degassing in vacuum, keeping the melt temperature low, do unnecessarily superheating. More superheat you do, more gas it will absorb from the moisture. So keep the superheating to minimum possible. Keep the mold dry or hot. Okay, and sometimes just waiting helps, but you have to wait, exactly know where to wait. If you wait enough, the gas will come out of the mold and vent out, if the venting should be good. Okay, so these are some of the things to handle the gas porosity in castings. How does a blowhole really form? You see two nice examples, nice for us. So we like to collect defective castings. So what is defective for you and headache for you is a nice for us, because we can understand that and analyze that. So you see two different examples of blowholes in, I think, ferrous castings, and in the second casting at least you can see the telltale mark of blowhole forming at the top, and you see a beautiful smooth surface. Characteristic surface of blowhole is smooth, unlike shrinkage, which is rough. Okay. Now why does the blowhole really form here? Look at the 4 pictures on the bottom. The metal is slowly rising in the mold cavity. The air is trying to escape, but pressure of the air is building up because air doesn't escape all completely. So pressure of the air and the gases are burning. Okay, other steam is coming out. All those are accumulating on top of the casting, and that pressure slowly builds up. The moment that pressure exceeds the metal hydrostatic pressure, your rho GH, the gas will enter the metal. Addition, I'm talking about blowhole gas here. Once it enters the metal, it's a gas bubble after all. Can you imagine a balloon sitting in a water tank? It will always try to float up. So the gas enters the metal, but it will also try to float up again. But in the process of floating up, if metal is solidifying fast, then the gas gets trapped and you get a blowhole. So if you have a high gas generation and high solidification rate, these are conditions for forming of blowholes. But if solidification rate is slow, then gas has time to escape again from the mold if venting is proper. Okay, so fast filling, fast solidification leads to blowholes. So what I mentioned to you was that blowhole will form when the pressure on in the mold cavity because of all those gases minus the gas pressure because of escape. If this exceeds the metastatic pressure, you start getting a blowhole. So, and if these equations are not getting too difficult for you, the gas pressure is nothing but pressure from moisture. They are all partial pressures of moisture and binder gases and additives and all those things. And air pressure is your back pressure of the air minus air escaping from your venting. Okay, so here is some example of actual conditions where the pressure in the mold is exceeding your hydrostatic pressure, and so it creates a condition for blowhole formation. Now, just for information, different types of core materials or binding materials. So, if you see, you are using a core oil, okay, or if you are looking at different, it is all for core oils only in this particular case. Okay, how much pressure is allowed, okay, before the blowhole starts forming. But we need to make the chart also for other kinds of cores which we haven't gotten data for. How to prevent the blowhole? This may be important for you. Okay, one is if you can somehow manage to keep the hydrogen content of the metal below about, let's say, 2 parts per million. Okay, nitrogen content is much more safe limit is there, so you can go up to 100 ppm. And manganese, permeability of the sand, if you can keep it good, okay, it should be more than 90, yeah, not less than 90. Okay, and I think the other both got reversed. Okay, moisture less than 4%, you can have conditions for preventing blowhole. It partly becomes it's a little more complicated than that. Manganese will affect your solidification characteristics, and then therefore you are allowing the gas to escape a little better and things like that. But little complicated that even we don't understand. We know that by experimentally manganese, if you keep the manganese little less than that, less than 1%, it reduces blowholes. The mechanism of that forming is still not very well understood. We only know experimental values of that. Could be one, but then the gas generation is coming from so many sources, and oxide is only one of that. So if you have induction furnace, and if you are in a dry season, okay, obviously you see gas porosity jumping in monsoon seasons, right?
Particularly in Indian foundries, majority of the furnaces are oil fired.
Cupola or oil fired, but oil fired where you have hydrocarbons, where you are putting the. Now, there is one interesting defect which is lab formation, and I want to talk about that. It's interesting because it happens because of the geometry and flow and solidification together, 3 factors coming into picture. So look, imagine the metal flowing into the mold cavity slowly, and once it enters the long horizontal portion, imagine the vertical velocity. It is going steadily vertically in the mold cavity. The moment it reaches the horizontal portion, the metal flows horizontally, and the vertical velocity almost comes down to 0, correct? It is filling up the horizontal portion. Only when the horizontal portion is filled up completely, then it again starts rising more. But because of that differential thing, okay, and if there is, supposing there is a pathway from the top to other side, on the last part if you see there is a differential temperature. The one part is frozen, the liquid metal is coming in, these don't fuse completely. So you have some kind of a lap. It's sometimes visible actually on the side of the casting. It happens because of differential cross sections. A certain cross section is increased and then reduced again, and there is a molten metal path coming to other side. Those two don't fuse completely. It's like a cold shut. You can say it is like a cold shut, except it is cold shut in a vertical direction, not in a horizontal direction. Now venting of course is important. I mean I don't have to talk too much about that. And if you do enough venting, and we'll talk about how do you vent from the critical things like cores a little later. But normal mold venting, the more you do, the better it is anyway. And so we'll just close it here. So essentially we talked a little bit about the gas sources and gas pressure build up in the mold cavity, and the moment the pressure exceeds your metal static pressure, it enters the metal casting, and the casting is freezing fast, then you form a blowhole. So how do you prevent blowholes? One is keep the pressure low. So keep all those gas contents low, okay, let the air escape nicely, don't have too much of excess binder material into that, don't keep the metal temperature too high, okay, and try to fill slowly. If you fill slowly, then air has time to escape from the mold cavity. So it's a fast filling and fast solidification is what creates a blowhole. And there is no discussion about the need for proper degassing and proper venting. These are essentials. Degassing is one thing that cannot be emphasized enough, especially in aluminum alloys, because almost everything else in foundry you can control something by design, but gas porosity you cannot control by design. You have to control only by process conditions, only by degassing properly and following all the rules of the game. Okay.